All right. Greetings, YouTube. Beautiful Mind here. This will serve as the lecture for week 5, Monday, for Calculus 1. We're going to be doing section 3.9, derivatives of exponential and log functions. I hope everyone has had a great weekend, restful and rejuvenating. We're able to stay on task. Exam 2 was due this past Saturday at 11:59. So just the main thing is just be sure that we're getting our assignments submitted promptly. If you're having any kind of difficulties, you have to reach out to me, because if you don't reach out, I'm not going to know. But we have tutors available. You have support. It's just a matter of speaking up and asking. I know that's the hardest part for a lot of students, but that's just barely the starting line. It's just asking for help. Then the race actually begins. But if you know where you stand, like what's going on. You know if you're getting it or if you're not. And like if you're not getting it and you're not asking for help, then you hadn't even made it to the starting line yet. And it's still, I mean, anything is still possible. Okay, anything is possible. You just have to push, and go for it, and like abandon fear. Unless that fear is actually serving you and allowing you to create the reality that you want to experience. If that fear is not serving you, I would suggest abandoning it. It's still, being aware and things of that nature, but a lot of times people do a lot of ignorant things out of fear, but that doesn't, I'm not saying don't be cautious. You still be cautious and still have a sense of mind to be aware of what's going on, but don't let that get in your way from what you need to do. You know what I mean? And I'm also talking to myself with all of this kind of talk. So that's neither here nor there. So let's take a moment to get into the material for today. So we'll go ahead and move into section 3.9, derivatives of log functions. So let's see what it says. So let's talk about the derivative of y equals the natural log of x. So from section 1.3, the natural exponent function e to the x is a one-to-one function on the interval negative infinity to infinity. Therefore, it has an inverse, which is the natural log. Okay. So inverse property, exponential of a natural log is x, and the log of an exponential of e to the x is just x. Y equals a natural log of x if and only if x equals e to the power of y. So those are just inverse properties of e to the x and natural log of x. So okay, let's see. So say we take the log function and we write it as an exponential in the form of x equals e to the y, right? So this is the exponential form of the log function, right, of the natural log. So then if we differentiate both sides with respect to x, the derivative of x is just 1. Derivative of e to the y is e to the y times y prime, or dy by dx, right? That's the chain rule. So then ultimately, the derivative of the log is going to be 1 over e to the y. But then earlier we said that e to the y is just x. So then the derivative of the log function is 1 by x. I like that little property. That was kind of fun. So then the derivative of the natural log function is 1 by x. Okay, so because the domain of the log function is 0 to infinity, this rule is limited to positive values of x. Okay. Okay. All right, let's see. So we have this theorem right here. It says the derivative of log of the natural log function is 1 by x for positive x, and the derivative of the derivative of the natural log of absolute value of x is going to be 1 over x for x not equal to 0. All right, because if it's negative, it becomes positive, and then, So if u is differentiable at x, and u of x is not equal to 0, then the derivative of the natural log of the absolute value of u of x is going to be u prime divided by u. Okay, so let's give this a go. We are here. Let's add a page and let's introduce our graph paper. Okay. So we're asked to find the following dy by dx for the following functions. So the derivative of log, so 1 over that. Okay. All right. Let me see. What are we looking like? That should be fine. So let's write it here. We have example 1a. So we have y equals the natural log of 4x, and we're asked to find dy by dx. Okay. So then d by dx of this y is going to be d by dx of the natural log of 4x. That's going to be, so the derivative of log is 1 over this thing times the derivative of that thing times, so in this case it's going to be times 4. And then ultimately we're going to get 1 over x. Okay. Let's delete that. Okay. I'm going to go with that for right now. I want to try to finish these out, then we'll look at the answers. So then example 1b. So we have y equals x times the natural log of x. Okay. Let's give this one a go. So again, we want to find d by dx of this y. So that's going to be d by dx of x natural log of x. Okay. So for a quick moment, ask yourself, do you realize which rule do we need to invoke here? We're going to invoke the product rule, right? Because it's a multiplication. So the product rule goes the first times the derivative of the second, so d by dx of this thing. So the first times the derivative of the second plus the second, which is this, times the derivative d by dx of the first, which is this, right? So if we account for those changes, the derivative of natural log of x is just 1 over x. So we're going to have x times 1 over x plus the natural log of x times the derivative of x is just 1, right? So then these two cancel. So then it looks like we finish with the natural log of 1 plus 1. Okay. Again, I'm just going to go with these for now, and we'll check it against the answers from the example momentarily. Let's look at example 1c. Our y is going to be equal to the natural log of the absolute value of secant x. Natural log of the absolute value of secant x. All right. So we got a lot of different things at play here. Okay. So we're asked to find d by dx of this natural log of the absolute value of secant x. I feel like there's a lot going on. I'm just going to kind of go with the natural flow and rhythm until I kind of reach a crosshairs or crossroads. Okay. So the derivative of natural log is 1 over itself. Let me look at something really quickly. Yeah. So this is going to be 1 over secant x. Let me think about the graph of secant. It's not going to be 0 anywhere. Okay. Times the derivative of secant x times d by dx of secant x. Okay. Now secant, I don't know offhand, but I'm going to rewrite it in terms of sine and cosine. Secant is what? 1 over cosine. So then we're going to have 1 over secant x times the derivative of 1 over cosine of x. Okay. So I think last time we said the derivative of cosine is negative sine. So this is going to be 1 over secant x times 1 up. We need to use another rule. It's not that straightforward. So instead of 1 over cosine, I'm going to rewrite this as cosine to the minus 1 in this fashion. So cosine of x to the power of minus 1, right? So then if we use a chain rule, the minus 1 comes down. I think this should be okay. Then we're going to have cosine of x to the minus 2. And then we're going to times the derivative of cosine is negative sine of x. Okay, so a lot of things at play there. Okay, let's put all this together. We got a double negative going on, so double negative becomes positive. We got 1 over secant x times sine of x over cosine squared x. Let's see, am I missing anything? let me see. If I did the bottom times the derivative of the top minus the top times the derivative of the bottom. Yeah, I think this should be fine. All right. Okay. So then, if we keep with that algebra, secant is what? 1 over cosine. So this is the same as cosine x times the sine of x over cosine squared x. Then one of these cosines cancels one of these. We're left with sine over cosine, which is what? Tan of x. Okay. So again, a lot at play there. I'm going to go with this though. I'm going to let that be. And then let's do example 1D. Okay, and we'll see how we did in a moment. So then D is the natural log of x squared over x squared. So we have y equals the natural log of x squared over x squared. Okay. So we're asked to find d by dx of this y, which is going to be d by dx of this natural log of x squared over x squared. Instead of use the quotient rule, I'm going to rewrite that denominator as a negative exponent, and I'm going to use the product rule. So this is the same as d by dx of x to the minus 2 times the natural log of x squared. Okay, so we got a few different things going on at play here. Just you have to do your best. So if I use the product rule, that's going to be the first, which is this guy, times the derivative of the second. So d by dx of this natural log of x squared. So the first times the derivative of the second plus the second, which is this natural log of x squared, times the derivative or d by dx of the first. Okay. So then let's do those derivatives. So then we're going to have this x to the minus 2 times the derivative of natural log is 1 over x squared times the derivative of the x squared is 2x. Okay. We're going to say plus the natural log of x squared. The derivative of x to the minus 2 is going to be negative 2x to the minus 3. Okay. I think this should be okay. Okay. So notice that these two are going to become 4. So 1 minus 4 is going to be a negative 3. So then on the left, we get 2 over x to the third plus we have negative 2 times the natural log of x squared over x to the third. I guess that's about the best that we can do. This is going to be 2 minus 2 natural log of x squared. We could use some log properties, but that doesn't really change anything, over x cubed. I'm going to go with this. We could change it up a little bit, but it's essentially going to be changes on this. At least as far as I can see for now. Okay, let's see how do we do. Okay, let's see how do we do. So for the first one, we got 1 over x and 1 over x is correct. Next one is natural log of x plus 1. Natural log of x plus 1. 10 of x is the next one. 10 of x, and then 2, essentially what we got, right? Because we can factor out the 2. 1 minus natural log. Okay, we got that one as well. Okay. So then next we want to explore the derivative of b to the x of an exponential. So a rule similar to the derivative of exponential exists for computing derivatives of b to the x. So instead of the derivative of e to the x, now we want to generalize for the general exponential. Okay. So what they did is rewrote the general exponential as e to the exponential of a log, and then apply the chain rule. So ultimately we get the following. The derivative of a general exponential is going to be that exponential times the log of b, times the log of that base, natural log of that base. Okay. Let's see if we can see this in action. Okay. Let's add a page right here. Okay. Nope, not there. Did we just do that one? I think I added a page in the wrong spot. Okay, I think we're better now. Okay. So find the derivative of the following. Yeah. So for example 2a, we have f of x equals 3 to the x, all right? So then f prime of x, the derivative is going to be itself times the natural log of 3. And that should be it. It's the chain rule. So remember, for an exponential function, the derivative itself, but we just need to tack on the extra part of multiplying by the log of the base. Okay. So then for example 2b, we have what? G of t equals 108 times 2 to the power of t by 12. Let me think about this one for a moment. Okay, so we're just going to use the chain rule a couple of times, right? So g prime of t, the 108 pretty much just comes in front. Now the derivative of an exponential is itself times the derivative of, so if you have that, that's going to be, the derivative of the exponent is just going to be 1 by 12 times the natural log of 2. We got to multiply by the log of the base, right? Let's see. 108 divided by 12. If it's 10, if it's 90. 108, right? So it's 9. So it's ultimately it should be 9 times 2 to the power of t divided by 12 times the natural log of 2. This is what I get. Okay, let's see how do we do. I guess we didn't need as much space as we thought. Example 2. Did I just... Oh, is example 3 in the same one? Why? Is that supposed to have the... Oh, that's the solution. Okay. So then 3x natural log of 3 was the first one. 3x natural log of 3, 9 natural log of 2 times 2, 9 natural log of 2 to the power. Yeah, this is good. Okay. All right, let's kind of keep it going. So in this example 3, it says table 3.6 and figures 3.65 show how the incidence of Down syndrome in newborn infants increases with the age of the mother. The data can be modeled with the exponential function this, where A is the age of the mother in years and P of A is the incidence, the number of Down syndrome children per total birth. According to the model, at what age is the incidence of Down syndrome equal to 1 in 100? According to the model, at what age, so solve for A, compute P prime, find P prime of this. So about 39 or 40. Is that just reading it? So about 40. All right, I just looked at the model for that one. Oh, they plugged it in. Okay, that's fine. So at what age, right? Okay. So we're going to solve for a, so if we set it equal to 0.01, okay, that's fine. So if we have, what is that? 1613000 over or under 1 times 1.2733 to the power of a, we want to know when will that equal to 0.01, right? So if we're going to solve for a, we multiply both sides by that. So then we'll get 1.2733 to the power of a equals, move the decimal to the left by 2, 1613 0. Okay. And then to solve for a, we take the natural log on both sides. So then a is going to be the natural log of that 16,130 divided by the natural log of 1.2733. Let's choose our calculator. Okay. So if we're going to use the calculator, we're going to say the natural log of 16,130 divided by the natural log of 1.2733. We get like 39, yeah, approximately 40, right? This is approximately 40 years old. Okay, so we've confirmed that one already. So that was part A. Compute P prime. So if P of A is 1,613,123 under 1 times 2733 to the power of A. So then that means that P prime of A is going to be, so that just comes out 613,000. The derivative of exponent is itself 1.2733 times the natural log of 1.2733. Okay, so that should be it. Let's just kind of rewrite it a bit and let's go ahead and add a page. Do we need another page? Not really. So this is going to be natural log 1.2733 over 1,613,000 times 1.2733 to the power of A. Okay. Then, let's see if I can get it to fit. Example 3C. P prime of 35 and 46. So then P prime of 35 and P prime of 46. So then P prime of 35, I would just do that in the calculator. I'm just going to say calculator for both of these. So we can just look here. Okay. So the general power rule, the derivative of general power is just going to be the exponent comes down minus 1. And then if you have to use a chain rule, it's the same thing, but then times the derivative of the inside function if we have to invoke the chain rule. So we're asked to compute the following derivatives. Okay. So for example, for A, we have y equals, what is that? X to the power of y? X to the power of pi. So then d by dx of y is going to be d by dx of x to the power of pi, which is going to be x to the power of pi. So the exponent comes down, it's going to be pi times x to the power of pi minus 1. Okay. If we have y equals pi to the power of x, so this is an exponential, so then d by dx of y is going to be d by dx of pi to the power of x. So the derivative of an exponential is itself pi to the power of x times the log of the base, natural log of pi. Okay. And then example 4c, we have y equals x squared plus 4 to the power of e. Okay. So then d by dx of y is going to be d by dx of x squared plus 4 to the power of e. That's going to be, so the chain rule first, right? So the exponent comes down, so it's going to be e times x squared plus 4 to the power of e minus 1, and then times the derivative of the inside function, so we're going to say times 2x. Two ex times x squared plus 4 to the power of e minus 1. Okay, let's see, how do we do? Okay. So for the first one, pi times x to the power of pi minus 1, pi x natural log of pi. And the last one is 2ex x squared plus 4 to the power e minus 1. Okay. Okay. Let's see. Let f of x be this. Find f prime of x. Evaluate f prime of pi over 2. So then for example 5a, we have f of x equals x to the power of sine of x. Okay. And they ask us to find f prime of x. What if we wrote this, instead of leaving it as an exponential, we wrote it as a log function? Let me see. So if it's an exponential, so the power rule, right? Let's do this. Let's see what happens. I'm kind of stuck here. Let me see. Hang on. Okay. I don't think that's going to work what I'm initially seeing. Yeah. So I think we just need the proper form. Give me a moment. Oh, okay. So this is the same as e to the power of the log of all of that? Okay, so we're going to pull that out of the exponent. Okay, so the target is... So first we're going to rewrite it before we... Because we have a variable in the base and the exponent. So this is the same as e to the power of the natural log of this thing, x to the power of sine of x. But then when we do this, when we take the log of a power, that exponent can come down, so that this is going to be the same as e to the power of sine of x times the natural log of x. Okay. So now we've gotten our variables in the exponents exclusively, instead of one in the base and one in the exponent. So now we're ready to do f prime of x. All right. So the derivative of e is itself, so this is still going to be e sine of x times the log of x. But then we're going to say times the derivative of the exponent. So we have to use the product rule. So the product rule is going to be the first times the derivative of the second derivative of natural log is 1 by x, plus the second, which is natural log of x, times the derivative of first, derivative of sine is cosine. Okay. So then ultimately, it should still be, I'm going to put the original back, so it should be x sine of x, x to the power of sine of x, times, we got sine of x over x plus the natural log of x times the cosine of x. Let's see if we can get something to cancel. I'm not seeing anything immediately. Let me look at theirs. So they still have x sine of x, cosine of x times the natural. Yeah, that's exactly what we got, right? Okay. Yeah. So that was a little bit funky. But the main thing there was because we had a variable in the base and a variable in the exponent. So we rewrote it so that the variable was only in the exponent and then proceeded, using the fact that the original can be rewritten as e to the power of the log. All right, so that way the variables were only in the exponent, then we treated it like an exponential. Okay. So then the next part, f prime of pi over 2. So then I would just say use the calculator there. I'm just going to say calculator, 5b. So that's a check on your calculator. Because we basically replace all the x's with pi over 2. Let me think about it. Sine of 90 is 1. Cosine of 90 is 0, so that second term is gone. That's a 1. Let me actually just do it. So if we say f prime of pi over 2, that's going to be sine of 90 is a 1. So then that's going to be pi over 2 times 1 over pi over 2 plus the natural log of pi over 2. Nope, that's gone, right? Because cosine of 90 is 0. So that second term is just gone. Delete. So all of that goes to 0. And we're going to be left with this. If we have pi over 2 over pi over 2, then it's just 1. Okay. So for that one, we just got 1. Let's see how do we do. Okay, we got 1. Okay. So if f of x is this, determine whether the graph has any horizontal tangent lines. So the slope of a horizontal tangent line is going to be 0. So basically what it's saying to do is find a derivative and set it to 0, right? Okay. So this is example 6. And we have what? F of x equals x to the power of x. So we might have to use that same technique again, right? So this is going to be the same as e to the power of the natural log of x to the power of x. But then we can rewrite that as e to the power of x natural log of x. All right. So then if we're going to find a derivative f prime of x, so again, the derivative of e is itself, e times e to the power of x log of x. And the derivative of the exponent, we have to use the product rule. So the first times the derivative of the second plus the second times the derivative of the first. Okay. So this goes to 1. So then ultimately we get x to the power of x times the natural log of x. Let's write it this way. 1 plus the natural log of x. Okay. So if this is the derivative, we got x to the power of x times 1 plus natural log of x. We want to set that equal to 0. A number to a power of itself. I mean, we can use that same technique to evaluate that, but basically we got to set each of these to 0 and solve. Okay, let's try it out just to see what happens, right? So if we say x to the power of x equals 0, or 1 plus the natural log of x equals 0. So then this first one, we can rewrite it as e to the natural log of, basically it's going to be x times the natural log of x equal to 0. So e is an exponential, right? So it starts off nearly horizontal and then it takes off in the exponential, but it never reaches 0. So it won't be equal to 0, right? So this one does not exist. There's no answer there. Then this is just what I anticipated, but I just wanted to explore. And then on the right, a natural log of x, a y value being negative, Yeah, we can take the log of a negative, right? So then the log of x equals -1. So then raise both sides to the power of e. So then x is going to be e to the -1. So then the horizontal asymptote should occur when x equals 1 over e, or e to the -1. Okay, let's see how do we do for example 6. So 1 over e. Okay, so we have this derivative of the log function. It's going to be 1 over x natural log of b. Okay, so if we took the log and wrote it as an exponential, let me see. So if we have x equals b to the y, take the dy by dx on both sides, that becomes 1. So here, this becomes 1. The derivative of this is going to be itself times the natural log of b times y prime, all right? So then we can divide both sides by this, so dy by dx equals 1 over this. And b to the y we said was x. Okay, okay. So that leads us to this theorem. All right, okay, let's give it a go. So we have example 7a. What's the time? So we have f of x, ouch, equals the log base 5 of 2x plus 1, right? So then f prime so x times the natural log of the base, right? So it should be 1 over 2x plus 1 times the natural log of 5 times the derivative of the inside function, which is going to be 2. So then, let's see, let's write it. Natural log of 5 times 2x plus 1 under, I think it's just 2. Can't say anything beyond that. Okay, let's see. I can't, yeah, that looks fine to me. Okay. And then example 7b. We have t of n is going to be n times the log base 2 of n. We could either rewrite the product as an exponential, but I think that's going to make things worse. So we're going to use the product rule. So then t prime of n is going to be the first. The derivative of log is going to be 1 over the natural log, 1 over x. So in this case, 1 over n times the natural log of 2. So that's the first times the derivative of the second, plus the second, which is log base 2 of n times the derivative of the first, which is just 1, right? So that's essentially what I get there. So just pretty much just using those formulas directly. Okay. So let's see, how do we do? The first one, 2 over the natural log of 5, 1 over 2x plus 1. Yeah. And then the second one is the natural log of n plus 1. Oh, there it is. Okay. That's a change of base formula. Oh, to get it to be the same, that's fine. The log of log base 2 of n plus 1 over... Yeah, those cancel, right? I totally omitted that. So that cancels that. Okay, this is fine. Now we could do a change of base, and it'll become the log of n divided by the log of 2. That's fine. Okay. These have been pretty smooth so far for the day, for me at least. Okay, let's keep it going. I think this might be the last one. So we have this, and we're asked to find f prime of x. Okay. I'm going to just go ahead and get myself some paper because I look like they're trying to go ham on this example. All right. So for example 8, so for example 8, we have f of x equals, we got x squared plus 1 to the power of 4 times e to the x divided by x squared plus 4. Okay. And they asked us to find f prime of x. I'm just going to use the quotient rule. So the bottom, so low d high minus high d low over low low. So the bottom is going to be x squared plus 4. Low d high times the derivative of the top. So if we take the derivative of the top, we got to do, well, let's do this, d by dx of this thing. There's a lot going on there, e to the x. So that's low d high minus high, which is this guy. And the derivative of the bottom, it's just going to be 2x there over the bottom square. So it's going to be x squared plus 4 quantity squared. Okay. So we do have another derivative to calculate. So this just comes down. So we have to use product rule and chain rule. We've got several rules going on there, right? So if we say the product rule, the first, which is going to be this, times the derivative of the second derivative, e to the x is just e to the x. First times the derivative of the second plus the second times the derivative of the first. Now we have to use a chain rule there. 4 x squared plus 1 to the power of 3 times 2x. That's the second times the derivative of the first. That's all of that. Then we still got that part over there. We're going to say minus that x squared plus 1. Okay. And then we're still going to do all divided by x squared plus 4 quantity squared. Okay, let me shrink this. I'm going to get this all on one line just for the sake of presentation. So like this, it's supposed to be here. I'm going to delete that. This can go under all of that. Let's undo. Okay, that's fine. So then, let's see if we can, all right. Can we get anything to cancel? That would be nice. Now we got the double x squared plus 1 that could be factored out. So let's see, there are 3 here and 4 there. Shoot. So, okay, we can get the following thing happening. We can factor out, it looks like we could factor out a x squared plus 4 to the power of 4 from the two terms on top. Now if we do this, we finish with, we took 3 from there. So we have e to the x times x squared plus 1 to the power of 1. Looks like we can factor out an e to the x from everything too. So let's get rid of this. We can put an e to the x here. So those are gone. That's left. That's gone. We got an 8x there. So it looks like we can say plus 8x. Okay, that's fine. Maybe they might factor. That's gone, that's gone. We're going to have a minus 2x there. And we are distributing that into both of those. That's fine. Divided by, we got this x squared plus 4 quantity squared. Okay. So then what can happen is 2 of these can cancel 2 of these. Okay. Let's see, we can keep going. Let's see what else, other simplifications we can do. We still have this e to the x squared plus 4. 8 minus 2 is a 6, so we have x squared plus 6x plus 1. I don't think that goes any further. And this is squared. We could combine those into 1. That'll be a 4 ultimately. I think it'll be a power of 8. 8-degree polynomial, or we can leave it like this. I'm going to leave it like this. Okay, let's see, how do we do? I can't seem to get anything going a little further. Okay. Looks like we are way off. Did I miss a log somewhere? Oh, we did need to take the log on both sides. Well, I guess because the x was in the exponent, I think I just totally got that wrong. Okay, I think I totally got that wrong. I think I missed the e to the x. I think it's because we have an x in the base and an x in the exponent. So maybe we can't do that. Okay. All right, well, I'm going to scrap that one. Okay. I think I'm going to leave my mistake in the notes just so you can see as far as the time. I'm going to put a big red X through it. I'm going to say no. All right. I think I'm just tired. Probably some other things too, but. So let's just look and see what they did. So first they took the log on both sides and then work with that simplification, right? So here's, because I think one, we have x's in the base and we have an x in the exponent. Let me see. So if we take the log here, right, this just stays. That becomes a plus. That is gone. That's out of the exponent, so that becomes just x, but you see it here. And then that persists as a minus, right? So then we have this. You can use the power rule for log, so the 4 can come down, okay? So now if we take the derivative, 1 over that, times the derivative of the inside function plus the derivative of the x, that's much simpler. Okay. Let me see, oh, because we took the log of f of x, I see. So when you take the derivative, we're going to get 1 over f of x, f prime over f. And then we got to incorporate the f back into it. Okay. Well, that was an adventure. Okay, so we finish with something like this. Were we off? Maybe not. I'm not gonna worry about it. So we can do this one if we need to, but they use the idea of taking the log of both sides, and I think it's because we had an x in the exponent and an x in the base, so we got them both to the same level and then proceeded. Okay, well that was an adventure. You can't win them all. Okay. I thought I had another page, but that's okay. All right. So I can't think of anything else. I'll go ahead and get some assignments posted for this. I think that's the last section in chapter 3 that we wanted to do. More than likely, we're going to move to chapter 4 next time. Okay. So I'll go ahead and glance at Moodle. If we are moving into chapter 4, which I think we are, I'll go ahead and load some assignments and probably a quiz for the week. Go ahead and get those assignments loaded. Okay. I'm available for questions. And we will end the session here. From one beautiful mind to another, enjoy the rest of your day. Peace.